I guess we can restart. Maybe. Yeah.
All right. Yeah, I'll just retake from where I was, I think. So, so basically, we see that for nonlinear systems are quite around us, and the nice things for us as a system identification community is that we develop tools that can basically work and can be applied on a wide range of systems coming from wide, diverse type of applications. And so these are a couple of types of applications I've been working on in the past. Now, if you look at nonlinear system identification, it's a problem which is much harder than linear invariant system identification. And why is that the case? Well, a nice illustration for that is given in the Control System magazine paper on nonlinear system identification. Basically, linear system identification is about characterizing a hyperplane in some large dimensional space. While nonlinear system identification is about characterizing a manifold. And that's, of course, a much more complex problem. Either you need much more data or you need much more assumptions. Basically, the nonlinear system identification is due to that, partially due to that, is definitely challenging. Nevertheless, we have made already quite some progress, and we have a wide range of models that we can use. And here I name 4 types of classes of models that we use for nonlinear system identification. We have linear parameter varying models, where we can embed nonlinear behavior in the linear parameter varying model using the scheduling variable. We have Rmax models, that is basically an input-output type structure, the nonlinear extension of Rmax. We have block-oriented models where we make interconnections, theories, interconnections, or parallel interconnections between static nonlinear and linear time invariant blocks to obtain a structured representation of a nonlinear system. And we have nonlinear state space models where we have a nonlinear state equation and then a nonlinear output equation as well. And during this presentation, I will focus on nonlinear state space models because they scale well to a multiple input, multiple output setting, and they give very compact representations of the dynamics of a system. Now, let's take a closer look at nonlinear state space models. If we have, here I represent the simple equations. Basically, we have on top the state equation, where we have the hidden states, which I assumed are not measured. And we have then an input, and the current state decides on what the next state is. And then in the output equation, the current state and possibly the inputs are used then to, through a nonlinear transformation, obtain the output. Now we have a lot of choices for these nonlinear functions f and g that are present. We can represent them as neural networks. We can represent them as a polynomial. We can use local linear models, and each of those models, they can be on top of that, in the previous equation, I ignored noise. So if we bring in noise in the picture as well, then we have also different choices to make. For instance, 2 possible choices is to use an output error noise form or an innovation noise form. So here on the left now you see the innovation noise form. Now, in the remainder of this presentation, I will first give an outline of what I consider the classical approach for nonlinear state space identification. And then I will go towards some challenges that are linked to the classical approach. And then I will address each of these challenges, and I will propose a couple of solutions. And those solutions, if you bring all these solutions together, that will lead to the introduction of the deep subspace encoder approach, which is basically the topic of this talk today. And then finally, some application examples of the deep subspace encoder method towards the end of the presentation. Okay, let's start with the classical approach. Let's, of course, I'll introduce that classical approach based on the identification framework. So we start with data. We have also a model structure that we have chosen, and there are some parameters in the model structure. We bring those two together in a cost function that tells us how different or how far away the model is from the data. And we optimize that cost function. Basically, we minimize the cost function by optimizing the parameter values. Once we have optimized it, we get an estimated model by combining the optimized parameter values with model structure. We validate that model. If we're happy, we can finish, we can test the model. If we're not happy, then we can go back, change the model structure, or change the input-output time series data. So that's basically the rough system identification cycle. Now, for nonlinear state space models, what are the classical settings there that I would advocate? Well, first of all, mainly use an output error noise structure. Why is that done? Because we noticed that when we do nonlinear system identification, the dominant noise, the dominant source of errors comes from actually model errors and not from noise disturbances. And we have noticed that an output error noise structure is more robust with respect to model errors. And then next to that, we need to parameterize the F and the G function. And historically, that's most often been done by using some kind of basis function nonlinearity representation. For instance, if we use here polynomials, then we end up with a polynomial nonlinear state space type of approach, which has been developed already over 10 years ago by Johan Paduart and has been implemented by Koen Thiels about 10 years, 5 years ago. Now, if we want to minimize the parameters, we use typically a cost function, which is a simulation error minimization cost function, where we use the sum of the mean squared error to express the cost. Why simulation error minimization? Well, we work with an output error noise setting, so that becomes automatically simulation error minimization. So basically the Y hat that you see here is not the predicted, well, it's actually the same as a one-step ahead predictor in case of an output error, but it's basically the simulation error that we consider here, or the simulation output of the model. And then optimization, that's typically done using some Gauss-Newton type of algorithm. For instance, the Levenberg-Marquardt algorithm is often used to minimize this type of cost function. Okay, so these are, I think, the three key ingredients of what I would call the classical approach. Other people might have other ideas about that, but let's bear with me and let's accept those at this moment. Okay, what are the challenges then? The challenges that I see is if we parameterize F and G, and we get more and more into more complex systems, so the number of states grows, the numbers of inputs grow, and the number of outputs grow, well, we have very rapidly the number of parameters that are being used to represent F and G. Definitely use black box identification. So then these number of parameters grow very rapidly with the state, input, and output dimension. That's the first issue. The second issue is that we have local minima. We minimize a simulation error. Even if F and G are parameterized by some linear combination of basis functions, this becomes a problem which is nonlinear in the parameters because we don't know the state and we simulated out. This depends on the previous states. So that becomes a problem which is nonlinear in the parameters. And then, of course, we always have the danger that we end up at local minima, and those local minima, they can be acceptable or they can be very bad. Next, we can also face instabilities during training. That can be on one end because for some regions of the data, for some regions of the parameter space, the model can become unstable, and then we get basically instabilities during the training. Or the gradient can also become unstable. So we have an exploding gradient, as they would call it in machine learning. And that, of course, again, results in bad training results. So we also need to resolve that. And then finally, we also have a computational and a memory cost. So if you do simulation error, you always need to simulate the full data record from the start till the end to compute the cost function. And then on top, we minimize using a Gauss-Newton-like algorithm that scales also badly for growing data. So there is basically no room for parallelization due to the fact that we have those transients or basically the dependence on the previous states that needs to be taken into account. But luckily, there are already many solutions that have been developed to tackle each of these issues. And so here in green, I list a couple of solutions that have been developed over the past years. If we look at large number of parameters, well, we can try to use more efficient type of representations of our nonlinear functions. If we look at local minima, we can work with smart initializations, or we can use methods that result in a smoother cost function. If we have instabilities during training, well, then the concept of multiple shooting has been studied and has been applied to get around that. And if we have computational error problems or memory cost, but recently we have been looking at the use of truncated simulation error. And from machine learning, we have also learned to use more and more stochastic optimization type of methods. So now with the question, how can we bring these elements? What are these type of solutions? I will discuss each of these solutions in a bit more detail. And I will then also discuss how these elements combine together in the deep subspace encoder approach. So what is a solution basically to solve this type of those 4 issues that I list here is by combining system identification and deep learning type of insight. And let's go through that step by step. So first, a large number of parameters. Let's take a look at obtaining efficient representations. Now, what is an efficient representation for the nonlinearities that we face here, F and G? What I propose to use is a feed-forward neural network parameterization for F and G. There are other choices that can be used, but for instance, there is also some people that have been looking, I think, for instance, Kim Batzler in Delft, that have been looking at tensor trains to have a low rank approximation. But from the literature, we know as well that neural network type of representations are very efficient to represent static multi-input static nonlinear functions. And why do we know that? Well, if we look at the results from the 90s, we see that the integrated square error when we use feed-forward neural networks to approximate a static function with multiple inputs, multiple outputs, basically decreases in so the integrated square error decreases with an order 1 over n, where n is the number of hidden neurons. What's important to note here is that that is independent of the number of input variables of this nonlinear function. While if we use a basis function approach, for instance, a polynomial-based basis function approach, then that error drops in 1 over n to the power 2 divided by the number of input variables. So from the moment that we have more than 2 input variables in a nonlinear function, we see that feed-forward neural nets approximate the error drops much faster by increasing the complexity of the neural network. So that's a motivation why we can continue with neural networks. Now, if we do that and we replace F and G by a feed-forward neural network, for instance, here I very schematically represent a 1 hidden layer neural network. So we have first a nonlinear layer where we have some activation, a layer of nonlinear activation functions. And then the output of these nonlinear activation functions are recombined to the right dimension using a linear layer where we basically just take a weighted sum of the outputs of the activation functions. I do that both for the state nonlinearity, so the F function, the state transition function, and for the output nonlinearity, so the G function in our state space equation. And then we get this structure, which is basically, well, this is a state space representation just drawn as a recurrent neural network. So in the end, the state space equation or the state space equation as we use it is a very simple recurrent neural network. If you write that down in the equations for a 1 hidden layer neural network, we end up with these type of equations. So what do we have here? We first have some weights. Those are the weights of the linear layer here at the output of the activation function. So sigma is the activation function that we consider, basically a nonlinear transformation that is there. That can be a Tensich type of function, that can be rectified linear units, there are many different activation functions that are being used. And that activation function has as an input basically a linear combination of the states and the input of the system that we consider. That is biased by some offsets represented as B, and then we have also a bias at the very output of the function that we have. So we have two biases to estimate. So what do we have? We have the weights and the biases that are the model parameters and that need to be estimated when we try to identify such a model structure. But before we do that, I will add one element here, and that is basically an explicit linear term in the equations. On one end, you can say this is similar to what residual neural networks do. So they use their skip connections. And if these skip connections need to change the dimensionality of the signals that they deal with, and they do that through, for instance, a linear matrix that just compresses the dimension. And basically, it's the same that we do here. It's also similar to what is happening, for instance, in the PNLSS toolbox, where automatically, because they use their polynomial type of expansion, they automatically also get explicit linear terms. Logically, if you think about it, it's actually also very, very natural to do that, because most systems are still dominantly linear and have smaller nonlinearities that are present. And it is not efficient to try to approximate a linear function using nonlinear type of activation function. So it's better in this case to just explicitly include it. If we do that and we take a look at how the network structure looks like now, well, it's basically the same. We just added a couple of arrows. So now we have here the skip connection that I mentioned. We skip the nonlinear layer and go directly to the linear layer here. But that's one of the skip connections, and we see this one coming back at every point. The equations are again largely the same. We just now have here explicitly the ABCD matrices coming back again in the equations. Okay, so that's what I propose to use as a more efficient type of representation that will keep the complexity of the number of parameters under control, because we simply use very efficient function approximation. Now, how can we use this model and how can we avoid local minima? And the first way to do that is to use a smart initialization of the parameters. And that's something that has been used already for many years. And basically, one of the main ideas is, well, we have here these ABCD parameters, which we recognize as basically, if we ignore the right part here, so if we ignore this part here, and we just focus on this part, well, this is just a linear time invariant model. That's good. We're very good at estimating linear time invariant models. So let's just use, for instance, a system identification toolbox in MATLAB, run the SSS command that gives us a state space, the state space matrices of a state space representation of the data. Well, that we can. And if we want a strong theory that explains us what is going on, then we can refer to the theory of the best linear approximation that explains us how this linear approximation behaves. So what is the idea? We do first an LTI approximation of the nonlinear system using the data that we have, and we push the ABCD matrices that come out of that LTI approximation as here in the parameterization here. The next step, of course, is we also need to initialize the W and the B, so the weights and the biases of the neural network. How will we do that? Well, we could choose all of them random. That's one option, and that would be the standard option. But then we have model that initializes at some other value than at an other behavior than the linear time invariant behavior. So what I propose to do is basically choose some of them random. Basically, actually everything which is coming from in the nonlinear layer, they are chosen random. So that results here in some library of nonlinear outputs, which can be chosen from at the first step of the optimization algorithm. And the other weights and biases we keep equal to 0. So at the first step of the optimization algorithm, we have that our state space neural network performance is equal to the linear time invariant approximation. But at the first step of the optimization, he can choose immediately from a range of nonlinear outputs to update the state equation and to update the output equation. Okay, so that's the first way to do parameter initialization. Now let's take a look on how that behaves. So as a small intermezzo, I'll have a look at the Bookwen benchmark. What is a Bookwen benchmark? Bookwen system is basically a mass spring damper system where there is one extra nonlinear term, which is here represented as a nonlinear spring, but it's basically in the equation, it's this term here, where it depends both on the mass position and the mass velocity, and it's given by this equation over here. And that's including that type of nonlinearity generates a hysteretic behavior of the system. So we see the hysteretic loop shown in the figure on the right bottom. So we have a Bookwen system is a hysteretic mass spring damper benchmark system that we consider. You can find a simulator of it on the nonlinearbenchmark.org website. What do? We use 8,000 samples for training. We use 8,000 samples also for testing. And those samples are generated as using a random phase multisign input, exciting the system between 5 and 150 Hertz. Now, if we do that and we run our method on it, so what do? We use an LTI approximation that is estimated in MATLAB, just using the standard settings, using the SSS command, and we fix the model order to equal to 3, because theoretically we know that it should be equal to 3, namely 2 states for the mass spring damper part and 1 extra state for the dynamic nonlinearity, the hysteretic nonlinearity. And then for the remainder, we use a 1 hidden layer nonlinearity to represent the f and the g function. And in that 1 hidden layer, nonlinear layer, we use 15 neurons using Tangen's hyperbolic activation functions. And we use the simple MATLAB deep learning toolbox using a Levenberg-Markar optimization to optimize the model parameters. And this we did for 100 times. Each time we have different random initializations to see how robust the approaches, the initialization approaches with respect to the random initializations. Okay, what are the results? First of all, let's take a look at the median result that we get for the state-space neural network initialized using an LTI model. And then on the left, we see the model output in the time domain. So we have here on the horizontal axis, we have time, vertical axis, we have displacement. In red, we see the output. In blue, we see the error obtained using a linear model. And in green, we see the error obtained using the state-space neural network initialized with the LTI model. So we see we have an extremely small error, which is very difficult to analyze in time domain. So let's take also a look in the frequency domain. So then in the frequency domain, we have the horizontal axis, the frequency, and then on the vertical axis, we have the magnitude in dB. In red, we see again the system output. In blue, we have the error of the LTI model, and in green, we see again the error of the state-space neural network. And we see that the error of the state-space neural network is 100 times or 40 dB smaller than the error obtained using the linear time invariant model. So this is an extremely accurate model, and we see actually it's very close to the noise floor of the simulations that have been used. So this is a state-of-the-art result. It's actually, to my knowledge, the best result using black box identification approaches on this type of system. But what we're really interested in is to understand if this initialization approach is working. And so what I did is comparing it to 2 other cases. So we have first on the right-hand side, the state-space neural network model structure without an explicit linear bypass. So the linear terms are not present in that model. And we have fully random initialization of the weights and the biases. So there we see that sometimes we get a good model if we go here to the bottom, but major part we get actually quite bad models because, well, remember, this is the RMSE error on a logarithmic scale. So the differences are quite large. If we do the same random initialization, but now with the neural network that has an explicit linear layer, we see already much better results. So you see that including this linear layer really, or this linear bypass really improves the results already. Still, there is a huge spread, but many more models become already close to high quality models here on the bottom. But then when we include the linear time invariant initialization, we see a drastic change, and we see that almost all models are performing excellent on the final results. So we see a very low spread of the 100 different models. So this is a very strong argument to really do a good initialization and think very well how you initialize your parameters, because that can have a very large difference. Okay, end of the intermezzo. Let's continue with the challenges that I've listed before. Other challenges another challenge that was present is instabilities during training. And that is linked also to local minima, because if you have instabilities, your optimization also gets stuck in a local minima. And the solution there that has been discussed in the literature is the use of multiple shooting. And it's also shown to have a cost smoothing effect. So what is multiple shooting? Well, let's first have a look at the problem. So for instance, here I depict a problem where our model in some range of the data. So we have in here we have the time axis, we have the output. In red, we have our data. And in blue, we have our model. And the model is doing good, but then in some region of the data, all of a sudden it runs into problems and the output starts, well, exploding exponentially. So basically we're entering in some unstable region of the model. So the model becomes unstable during training. That's very annoying. And what can we do about it? Well, one way that has been found to work around that, and it works, this is now the case for an exploding model output. For exploding gradients, you can have a similar reasoning. One way to do is to break the data sets in parts and restart the simulation at different points. So that's been already applied several times in the past. I refer now to a paper here of Jan Kuiper, but there are also a couple of papers before him that have been doing this. And then, of course, when we do that, we can use a zero or an estimated initial state to restart the simulation. So, for instance, here I break the simulation in the middle, I restart, and then we see that for a while it's going good again, but then he ends up again in some unstable region and we start exploding again. So here we have 2 sections, we can have 4 sections, we can have 8 sections, we can have as many sections as we want. But every time we need to restart the simulation, we need to estimate an initial state, or we start from a 0 initial state, but then we have transient errors. The nice thing is that actually this approach of using multiple shooting has been shown also to have a smoothing effect of the cost function. So if we use, here I used a large type of 500 samples, but if we use smaller section of 5 samples, for instance, it has been shown that that has a smoothing effect on the cost function. And that's very interesting because that means that we're less prone to local parameter, to local optima. Okay, so that's interesting. And actually in the next approach, we will drive that towards, let's say, an extreme form of that. So to reduce computational and memory cost, one of the solutions that have been discussed in the last 2 years is the use of truncated simulation error. Now, what is truncated simulation error? In the classical loss function, we have the simulated model output. So we simulate the model from time instance 1 till the end. So if we have n samples to sample number n. But yeah, why should we do that? Why can't we use just a small section of the data and start at time instance k1 and just simulate to time instance k1 plus t minus 1? We could do that, and we could calculate the cost on that small portion of the data. And then, well, we can start at k1, but we can also start at time instance k2 and compute the loss again. And we can do that at a whole set of time instances, K1, K2, K3. They can be randomly located in the data. Those sections can overlap, or they can be perfectly following each other up. There are many different options. And if we do that, we can reformulate the cost function as I show here below. So we now have a cost function which sums over all possible starting points that we consider. And from that starting point, we then simulate forward in time for t steps ahead. And this is actually an extreme form of multiple shooting, where we reformulate the whole cost function as a truncated simulation error. But actually, it's the same as multiple shooting, just that now we have possibly overlapping sequences as well. So if we look at this truncated simulation error, what do we see? Well, the computational cost can be lower, because now we have a sum over the different sections or the different windows of simulation length t. And each of these windows, each of these sections are independent from each other when we simulate. So we can simulate them in parallel, which means that the computational load possibly drops to order of t instead of order of n, if you can make full use of parallelization. On top of that, gradient explosion is cancelled, similar to what multiple shooting did, because you have a fixed length, and basically the gradient doesn't get the time to explode if you choose that length small enough, or the model doesn't get time to really become fully unstable. Well, fully unstable, it's not really correct system theoretically, but the output doesn't get time to become not a number, let's say, computationally. So everything stays better under control. That results automatically, due to the results on multiple shooting, also to its good on cost function. And we have shown as well that if you overlap these data sequences, so if you allow overlapping data points, so in the extreme, you just take every data point as a possible starting point of a section, then you get also a higher data efficiency in the terms that the variance on your cost function or the cost function will converge faster to the expected value of the cost function when you do that. And the nice part, the most important part actually, is that you can, since we have here these independent starting points here, we can easily use batch or stochastic gradient descent optimization. And that allows for a very efficient use of memory while optimizing. You don't need to have all data in memory. You can make computations on parts of the data, and you don't need to run through the full data step to only make one optimization step. You can have very many optimization steps by only running once through the data set. So that's a very efficient use of basically the data when optimizing. It's a method coming from the machine learning community. So how do we bring all of these together? So we have seen efficient representations, we have seen smart initialization methods, we have seen cost function smoothing through multiple shooting and truncated simulation error. And then using the truncated simulation error, we could also work with stochastic optimization methods. So the way to bring them together, or the way we did it, is by formulating what we call the subspace encoder. So we take a state-space neural network model. So that's our efficient representation, which we can possibly initialize using a linear time invariant approximation or not. And then we unroll that state space equation, t times forward in time. So then instead of having a recurrent neural network, we have a deep feed-forward type of neural network. And then, of course, we need to estimate the initial state to start our simulation from. There we will propose an encoder function. And then we can formulate a truncated simulation error cost and optimize that one using a mini batch optimization approach. So let's go through this again step by step. Our state-space neural network, so we use a representation, as I mentioned before, using an explicit linear part, ABCD matrices. Now we unroll that one. So what do I mean by unrolling? Well, instead of having the recurrent form, we just say we start at x of k, we take a step f, we get xk plus 1. If we apply f again, we get xk plus 2, and so on and so forth till we're t steps ahead. And at each point, we can have the output function that delivers us the output. So this is basically a deep feed-forward neural network where the same function comes back over and over again. The question is now how to retrieve the initial state. And there we can do a zero initial state we can use, but that is a lot of transient errors. And yeah, transient errors, if you have short sequences of t steps long, is a problem. So that's not a good way to go. We can use, we can add the initial state to the parameter vector and estimate the initial state. But if we really bring this multiple shooting ID to the extreme, we have so many initial states to estimate that the growing parameter vector becomes a problem. And so what we propose here is to use an autoencoder type of inspired initial state estimate. Now, what is an autoencoder? An autoencoder is coming from deep learning literature where they try to find a low dimensional representation or of a high dimensional type of data set. So we have here high dimensional I of k data set as an input. Then there is an encoder function that needs to be trained that gives a low dimensional z of k features. And then we have a decoder that makes sure that from those features, we can reconstruct the data we start from. So we get an estimate of the IK data. So that's the encoder, decoder, an autoencoder type of function. Now you can think, okay, we have as a data, high dimensional data, we have the past inputs and the past outputs. We can push in there. That needs to be compressed into C of k that will become our states. And it will be, it needs to be able to again represent the past inputs and past outputs. That could be one way of thinking. It's not very logical because we are dealing with dynamics. Our input is actually not dependent on the state, so we need to reformulate it a bit. That's been done 2 years back. Well, actually, it's just published this year, the Automatica paper by Daniele Masti and co-authors, where they used a variation of the autoencoder. So they use past input-output data, which is encoded towards the state. And that state is such that it can recreate the past, the current, and the past outputs again. But at the same time, they make sure that the state can predict the next state. And this prediction of the next state should be the same as the predicted state by the autoencoder function. Now, this is one way to go, but it has, according to me, some challenges. It requires multiple cost functions. You need at least, when you start to model the state space equations like this, you need to combine your cost functions from 3 different terms. And the states are not estimated really to do a long-term prediction of the system. It's only a one-step at prediction that is taking place. So how can we improve this? Can we make this more well straightforward? And the idea is to integrate the encoder in the main estimation problem. So instead of here we have this unrolled state space neural network, what do? We add here an encoder function. Well, the encoder function is actually a type of reconstructibility. From the past input and output, we reconstruct the state. And then what comes behind is our decoder, and we decode towards the current and the future outputs of the system. So really, we focus here now on the long-term prediction capabilities of the input of the state space model. And the nice thing is that now we have one cost function to rule them all. So we can estimate the parameters of the state equation function, of the output function, and of the encoder function all together. Because a better encoder gives a better initial states, which will lower the error because we have less transients. Of course, a better output mapping will be directly give a better estimate of the output because that is direct link towards the data. And if our F function is not good, we'll not have good long-term prediction. So the F function will also be optimized by this type of cost function. So that's good news. And that's basically the model structure that we will use now. So if we summarize that, as a model structure, we have an autoencoder, we have an encoder followed by the unrolled state space neural network. And here we use still an output error noise structure we're focusing on simulation error. As a cost function, we have a truncated simulation error minimization that results in a more smooth cost function that is also very computationally efficient and memory efficient. And as an optimization method, we use a mini-batch gradient descent with early stopping type of optimization methods to have a nice regularization effects as well, and to have, again, nice memory and computational efficiency. And yeah, okay, these are the advantages that I mentioned. Some extra elements to mention as well is that this scales very well to multiple input, multiple output data, because we have basically the neural network representation. And due to the smoothness in the cost function, actually, we don't necessarily need to start from an LTI approximation to initialize the parameter values. We observe that it works very well from completely random initialization. We have shown consistency for this type of method. Of course, not consistency to the true system parameters, because there are identifiability or there are equivalence classes that is possible. So it's a consistency to up to an equivalent set of the model representation. Now, there are many extensions that can be done and that have been implemented already. So we went from an output error setting to an innovation noise setting as well. You can go from discrete time to continuous time. Instead of considering time series, you can also consider video sequences of spatial temporal data. And we don't need to stick to a nonlinear state space type of representations. We can, for instance, also use other type of representations of F and H. And an example here of this is published in a paper where we use the same approach to identify a Koopman model. So let's now discuss some examples. I see I don't have that much time anymore, so Xavier, please interrupt me if I need to wrap up. But let's start with some examples. I've prepared 3 examples. We'll see how far I get. First, I have an example of using the vanilla subspace encoder the way I implemented it here on the Wiener-Hammerstein benchmark. We have results also on spatial temporal data using a spatial temporal encoder, and then final results using a Koopman modeling approach, so where we change the representation of the dynamics on the Silverbox benchmark dataset. So let's start with the Wiener-Hammerstein. Wiener-Hammerstein benchmark is a system which is comprised of a linear time invariant model followed by a static nonlinearity followed by, again, a linear time invariant model. And each of the linear time invariant blocks are third order low pass filters, and the static nonlinearity is a one-sided soft separation obtained by combining resistors and a diode element. We have 100,000 data points for validation and training, and we have 88 data points in the test set. We used 80,000 samples for training and 20,000 samples for validation. What type of model did we estimate? Well, we represented the static nonlinearities, so the F, the H functions, using a one hidden layer neural network with 50 neurons and a Tanzig activation function. We used 50 past inputs and outputs in the encoder, 6 states according to what the prior knowledge of the system will give us, and we predicted 80 time steps ahead. And we used a completely random parameter initialization. And these are the results we get. So on the left, we see again the time domain testing results. And yeah, basically what you see is that this is completely flat error. So the error in orange is completely flat, so you don't see much. It's extremely small compared to the output, which is to be expected. Other methods have that as well. So if we look in the frequency domain, what do we see here? In red, we see the spectrum of the output of the system. In blue, we see the error that would be obtained using a linear model. And in green, we see the error that is obtained using the encoder in this work. So starting from completely random initializations. If we compare that to another model with a much more structured representation of the system, the nonlinear LFR model, we see that we're doing slightly better than the nonlinear LFR model as well, which was initialized starting from linear time invariant representations. If we compare it to the other results that have been obtained so far, we see that we're doing about 10% better than the best results. But that's not the most important part. The most important part is that this shows that this type of approach works very well. And compared to the previous methods that were often including already very strong knowledge about the structure, we obtain similar results. Or compared to other methods that use much more strong initialization methods, for instance, using a linear time invariant model to initialize the parameters, we obtain also better results than that. So that's very nice. Then another example is together with Jan de Kuiper from Indy VUB. We have worked on modeling a spatial temporal system. So basically what we have, take for instance, we have that we would have a wing which is in an airflow, a constant airflow, and this wing would move up and down, and we take a side view. Well, this we have simplified. We have now a cylinder which is in a constant airflow. Cylinder moves up and down. There is a sine sweep input for the position of the cylinder, and then we observe the flow of the fluid after the cylinder, and then we get vortices there. So we get, what we measured is actually the pressure and the x and y velocity after the cylinder on a grid of 41 times 45 points. So that's 1,800 points times 3. So those are basically 5,400 outputs that we're having. And we have one input, the movement or the position of the cylinder. So this is an extremely high dimensional output. And what we did is, instead of using a fully connected neural network, we pushed in here also convolutional neural networks in the encoder and in the output function to make use of the spatial temporal or the spatial relations in the data. And we compared that also to a fully connected version. The model has 10 states. We used 3 past inputs and outputs in the encoder, and we predict 30 times that set during the in the cost function. And then if you look at the results, so on the left, we see the measured output velocity, measured output vorticity, the vorticity obtained using the fully connected neural network model, and the vorticity obtained using the convolutional neural network model we see here. And then on the bottom row, you see here the residual errors you will see when I run the video. And here on the left, you see the instantaneous normalized RMS error. If I run this video, you see basically that the two models are very similar or very close to measured data. So that's already a great result. Remember, this is simulation. This is not one step at prediction. So we get an extremely high quality simulation model. And you see as well that the errors obtained using a CNN encoder and output function, we get lower errors compared to having a fully connected neural network. This is also represented in the normalized root mean square error on the left. You see that after some time, this error will spike up. Why is that? Well, because this type of system, actually, when you keep the cylinder still, so no input, well, then this system starts oscillating from itself. There are automatically still vortices that are present there. And of course, so that's an autonomous system. If you have a slight difference in phase, so we're now in that region, if you have a slight difference in phase, then you go back. If you have a slight difference in phase, what we have is that we have a large error. But if you would start the method simulation directly in this region using the encoder to find the initial states, we see that we get again an excellent fit. And then finally, Koopman, embedding the Koopman dynamics. So what we can do there, we applied this on the silver box data. So that's basically a forced stuffing oscillator. We have again a multi-sign validation, training, and test set. And we have also a arrowhead test set where we see also a small range of data where we're extrapolating the model. Now we use a Koopman model. What is the Koopman model? Well, the idea of a Koopman model is to embed the nonlinear dynamics in a linear model by lifting the states to a high, possibly infinite dimensional space. So if we have here a nonlinear state space equation, by using a nonlinear transformation on the states, we go to, instead of having this nonlinear function f, we have this linear relationship between what they call the observables or the lifted states that are present there. And it's shown that that can be done for a wide class of nonlinear systems. Now, if we want to do that, we can easily embed that in our subspace encoder. Basically, what we did is now that we have this type of dynamics that we include in F and H. So we have a linear A matrix, a linear output matrix. What comes also out of the recent results that we obtained with Christie is that this B matrix, that one should actually be state and input dependent. So it's not completely a linear model, it's more like a linear pairing model that we obtain. So this is the type of model structure we use. And we can easily embed that here because in the implementation of this approach, we make use of automatic differentiation. So we can easily embed any type of form of dynamics, and the differentiation and the automation is taken care of for us automatically. So we do that. We use 20 states. Normally, this system has 2 states, so we use 10 times more states. As I said, we lift it to a higher dimensional state space. And then the results that we get are extremely good, I would say. So the validation that we obtain on the multi-sign data set is very low. So we see that here on the top. So we barely see it again. So the test set normalized error is 0.5%, which is a state-of-the-art result there. On the arrowhead, we see that it's very low for a very long time, and then it explodes towards the end. That's the extrapolation that's going on there. Since we use a nonlinearity representation, which is different from the cubic nonlinearity, which is truly present in the system, we run into problems here. All right, so to wrap up, I hope that I could convince you that by using this deep subspace encoder method, the neural networks, multiple shooting, a state encoder, or reconstructibility map, and batch optimization in a very efficient method to identify nonlinear system due to enhanced cost function smoothness, a good scaling with dataset size. You saw the spatial temporal example, and state-of-the-art benchmarking results. So all of this is implemented in a Python deepest them as well. Thank you for your attention. Thank you for the opportunity to present.
Thank you, Martin, for this nice presentation. Yeah. Oh. Thank you for this nice presentation, Martin. So, well, yeah, we can have some questions. Anyway, we are not so bound with the time. So, Martin, so please, yes. Just Vincent, just open your mic and ask your question.
Well, thanks a lot for the presentation. I had a few questions that might be somewhat technical or not. The first thing is that you showed a lot better result on the first test bench with a linear part plus the arctangent or the tangent H function.
Oh, no.
Naturally any kind of linear behavior in there. So maybe if you use nonlinear functions that embed directly some kind of linear behavior, you might be able to be less sensitive to the initialization, I guess. Or
that could be the case. So I think we're talking basically about this structure right here.
Yeah,
so, indeed, if I would use a rectified linear unit, you could say then I can initialize this network that can be done. That has been explored in the paper by Marteen Schoukens in the beginning of the 90s, and I've revisited that in my ECC paper. Okay. I didn't use rectified linear units, but I just initialized in the linear range of the Tanzig function, because that one is also a linear range. And what I observed is it doesn't improve the results. It improves the results compared to that for sure, but it's still much better to have explicitly a linear byte.
Yeah, and I guess the test bench also have quite a strong linear structure in the hysteresis that you showed. And actually it might be even good if you just extend the process such that you have an A matrix, but you could have a whole part which is, for example, a polynomial approach, like let's say cubic approximation. Then normally what you would expect that the rest of the nonlinear function should be quite null. And maybe this is why this random optimization around 0 is good. And then you could remove the cubes, then remove the squares, and then remove the linear parts, such that basically the initialization plays less role. So I think it might be able to be extended. So now you have the linear part, but you could have also a square part, cubic part, and so on,
well,
and remove them stepwise.
If you start to do that, then you're basically doing first polynomial nonlinear state space and then running here. I don't think that will have much because in the end, polynomial nonlinear state space is initialized in the same way as what I now showed here to initialize. So we would start from the same type of starting point. So I don't think that will give much better results. With the additional problem that PNLSS has as the big problem of exploding number of parameters if you take a full black box type of approach.
Okay, and I had just maybe. I guess it's very technical, so it needs a very short answer. I guess you cannot go in detail in there. But what I know about neural network is that there's this backpropagation algorithm from the error. And actually in the structure that you use where the states predict the outputs, is there some hard technicalities in doing some backpropagation? Because you need to backpropagate the decoder, but at the same time, you need to backpropagate on F. And I don't see straightforwardly how you can do the backpropagation on both the path, on the yellow path and on the purple path. Yeah. So is that technical or is it kind of straightforward?
This is standard backpropagation in PyTorch here.
Okay.
We didn't change anything because in the end, we have our cost function, which is the actual point we start the backpropagation from, and then we just flow through the different layers till this point here.
Yeah, but we see
these are just different. Sorry, go ahead.
No, you're go ahead. Sorry.
These are just different layers of a deep neural network. So we're just flowing back step by step through the deep neural network.
Okay.
So it's very standard.
Cool. Thank you. Thanks.
I know Rachid has a question, but I see François has also a question. Maybe he can speak or I can read this question. François? Oh, well, I read the question. Do you think your approach can handle time delay on the dynamical system?
We haven't really tried it much yet. I've a student of mine has applied it on measurement data where we know there was a time delay present, but we just took enough states and then let the extra states approximate the time delay. So it's a bit of a dirty approximation there. So we haven't tried to really estimate the time delay. But in principle, I think that should still be possible to do that. Because we can easily extend it to continuous time and then have a continuous time type of time delay as well in there. So I think it should be possible, but I haven't looked into technicality. So it might be that there are some surprises when we do that. Definitely with respect to local minima, because from what I remember, those type of optimization problems have extremely strong local minima.
Okay, thank you, Martin. So Rachid,
I have a quick question, and then I will have a comment also. Can you go back to the slide number 38, because I didn't understand very well the difference between the middle one. Actually, the random initialization is okay, LTI initialization is okay, but the middle one, I didn't get it.
Yeah, so the difference between the two right ones is the difference between this model structure. So this is the middle one where I use this model structure and I use a random initialization for the model structure where we have an explicit linear part, compared to the model structure where we don't have the explicit linear part.
Okay, fine. That's fine, thanks. And then I have a comment. I think you should be careful when you do spectral comparison, because you are dealing with nonlinear models. And we know from Volterra series analysis that spectral, when you try to plot the frequency response, then for a bilinear model, you have 2D plots. For trilinear models, you have 3D plots. So
I don't show the spectral frequency response function. I just take the spectral representation of a signal here. So there is nothing special that takes place here. So this is just the FFT of the output signal.
Okay, fine. So, thank you very much.
And then we have a very last one. We could continue this discussion. I had also some questions, but so Philip, the floor is yours for the last question. And then we'll have to go to Abir's presentation. Go ahead, Philip, we don't hear you. Maybe you can type your comment, your question into the discussion if it does not work. How do you choose T for the horizon? That's the question of Philip.
That's currently is a bit the black magic. Well, it's fairly robust. So we analyzed that, but in the end, it's fairly robust on how to do it. If you want to go towards simulation error, really, then just take it a couple of times the time constant of the system. Then you're actually already fairly well approximated simulation error. But if you really want to tune it such that you make use of the smoothness improvement of the cost function, then it's trial and error right now. So we don't have a strong framework yet to tune that.
Okay, thank you. Nice.
So I think I think I can talk to for everybody here, and in thanking Marteen for his very nice presentation. And so thank you, Marteen. And so now we will have to go to we'll go to the second presentation, which is given by Abir, and it will be on identification of fractional system when they are multivariable. So